Welcome back to a course on complex analysis. We are talking about the concept of complex integrals. As a continuation to the previous lectures, in this lecture also we are going to continue our discussion with respect to complex integrals. Okay, in the previous lecture, in the previous few lectures, what did we actually deal? So first we started with the concept of integrals of the function integrals of the complex valued function when it is parameterized, right? This is what we initially begin with. Then we have extended it to the concept of contour integrals. So contour integrals means what? You are asked to integrate a complex valued function over a curve. So this curve is parameterized and we convert this integral into integral of the previous one. That is, it will be changed into integral a to b f of z of t z prime of t dt. So we convert this integral into it. Okay. So this contour may be any form, maybe in any form, and we have seen few more results. That is to estimate the value. Okay, to find the upper bound of integral value, we had the ML inequality. Then we had the Cauchy's theorem, and this theorem tells you that integral over a closed simple contour to any analytic function is 0. This bears the integral value 0. As a consequence of this Cauchy's theorem, we have seen few corollaries results, and based on it we have worked out few problems, right? With that ideology only, we are going to derive some fundamental theorem, that is Cauchy integral formula. Okay, here we have a function which is analytic everywhere inside and on a closed simple contour C, which is taken in the positive sense, which means what? In the anti-clockwise direction. And we have suppose we have a point which is interior to C, then the function evaluated at the point z0 is equal to 1 upon 2 pi I integral over C f of z dz upon z minus z0. Okay, so when you treat your f of z upon z minus z0 as your whole function, what? So this function is not analytic at all the points because it has a singularity at z0. So if it is so, then how are we going to integrate this integral? So for which only we have this formula, and this is okay. Let us mark this as equation 1 and proceed with the formula, and in the due course I'll tell you how and when to make use of this formula to work out the problems, right? So the proof, right? Okay, it can also be written as equation 1 can be written as integral over C f of z dz upon z minus z naught equals 2 pi I f of z naught. So this is the easiest way, this is in the easiest format which we can prove. Okay, now let us begin. Let 0 denote the positively oriented circle absolute of z minus z naught equals rho, where this rho is small enough. It has to be small enough such that C row is interior to C. Interior to C. Okay. Suppose if you have, mm, if this is your closed contour C and this is your point Z naught somewhere inside it, you will have to choose row in a such way that this is there. This is completely inside C. Okay, we'll have to take in this way. Take this X and this is Y. So after taking this, let us examine about the uh, function. Since f of z upon z minus z naught is this quantity, this entire quantity is analytic between 0 and c. Since this is true, by the deformation of paths, what we can write? Integral over c f of z upon z minus z naught dz is same as that of integral over 0 f of z upon z minus z naught dz. Right? So we have this one. Okay. So with which, what are we going to do? Uh, so with which, what I'm going to write is that integral over c f of z dz upon z minus z naught. I'm just adding and subtracting a particular quantity on both sides. So minus f of z naught integral over 0 dz upon z minus z naught, which is equal to integral over 0. Already what we have here, f of z dz upon z minus z naught minus f of z naught integral over 0 dz upon z minus z naught. Since this is a constant, you can take it inside. Okay. And what? F of z dz upon z minus z naught minus integral over 0 f of z naught dz upon z minus z naught. We can combine these two integrals. So when we combine, this is integral over the 0 f of z minus f of z naught upon z minus z naught dz. Right? So this is what we have. Okay. So we mark this as equation 3. And we know that integral over 0 dz upon z minus z naught is 2 pi I. If you are not sure of how we get this, you just do the parameterization and do the thing. Okay, your z minus z naught, when you talk about this one, you'll have to parameterize and see what how it happens. We just worked out this one as an exercise. So this is quite simple. So using this, what are we going to get? So equation 3 becomes integral over c f of z dz upon z minus z naught equals minus 2 pi I multiplied with f of z naught. So this is what we get, right? Equals integral over 0 f of z minus f of z naught upon z minus z naught dc, and we mark this as equation 4. Right? So now we will make use of the analyticity of if given f is analytic, therefore f must be continuous basically, right? Because analyticity will imply differentiability and differentiability will imply the continuity. Since this is continuous, thus at z naught, this ensures to a positive number epsilon or what. So thus at z naught, for every epsilon positive, there is a delta positive such that absolute of f of z minus f of z naught less than epsilon whenever absolute of z minus z naught less than delta. Okay, so this happens. Then let the radius rho of the circle 0 be smaller than delta. Okay, we'll have to choose rho in such a way that it is smaller than this delta. Thus absolute of z minus z naught, which is equal to rho, which is smaller than delta, when z is on 0. Okay, so here the inequalities shall be marked as equation 5. With the help of 5, what we can do, so integral absolute of integral over 0 f of z minus f of z naught upon z minus z naught dz is smaller than what is the estimate absolute of f of z minus f of z naught upon absolute of z minus z naught and length of this length of 0, that is the perimeter of a circle, that is 2 pi rho, right? So this quantity is, the numerator quantity is less than epsilon and the denominator quantity is equal to rho, and we have 2 pi rho, so which is nothing but 2 pi epsilon. Okay, so since epsilon is arbitrary, we get absolute of integral over 0 f of z minus f of z naught upon z minus z naught dz is equal to 0. When this is equal to 0, the inner quantity must be equal to 0. So now, with the view of equation 4, by equation 4, we get integral over c f of z dz upon z minus z naught minus 2 pi I f of z naught. Absolute of this quantity is equal to 0. This proves integral over c f of z dz upon z minus z naught equals 2 pi I f of z naught. So this is what we intended to prove. That's it, right? So based on this, let us work out a problem now. As said, let C be the positively oriented circle, absolute of Z equals to, since the function f of Z, actually right, so this is given, find integral over C dz upon 9 minus C square Z plus iota. Okay, we'll have to find out the value of this integral. Okay, how to solve this? It's quite simple. Here, the integrand is Z equals 9 minus Z squared Z plus iota. Okay, the singularities are given by 9 minus Z square multiplied with Z plus iota equals 0. This can happen only when Z equals plus or minus 3 and Z equals minus iota. Okay, we found this one. Then look for the given contour. So the given contour is a circle of radius 2. Now try to identify how many points of this singularity are lying on this contour or inside this contour. Your 3 is somewhere here, minus 3 is somewhere here, minus iota is here, right? Only Z equals minus iota lies inside the circle, absolute of Z equals 2. If this is so, we can write this as integral over C Z dz upon, actually Z upon 9 minus Z squared dz upon Z plus iota. Okay, so this is what, then your integral can be written in this way, right? Here Z upon 9 minus Z square is analytic in the specified in the given region. Then by Cauchy integral formula, okay, so taking f of z as z upon 9 minus z square, we get integral over c z upon 9 minus z squared, or we can simply write the given thing itself, z dz 9 minus z squared z plus iota equals 2 pi I times of f of minus iota, right? It is 2 pi I. What is f? It is z. In the place of z, we'll have to substitute minus iota, 9 minus of minus iota whole square. So iota and iota becomes minus 1, and we have this minus, so numerator becomes 2 pi and the denominator is 9 minus of minus 1 is plus 1, so it is 2 pi upon 10, which is pi upon 5. That is the integral value. Okay, so this is how we'll have to make use of the Cauchy integral formula to evaluate the integrals. Okay, I told you people that I will tell you when and how to make use of this integral formula to evaluate the integrals. Right, this is happening here, and okay, in the next slide is devoted to discuss about the extension, but okay, I'll tell you one more ideology as well. Okay, so this is not specified here, but I'll tell you, I'll try to give it in a short way. Okay, over the same circle, if you are asked to integrate z upon 1 minus z squared, suppose if this is your integral, then inside the circle you are able to identify the points 1 and minus 1, right? So both of the singularities of this function are inside it. In this case, what you do is that you just take this to be z upon 1 minus z and 1 plus z. You consider this way, and you will have to split this integral into two things. That is integral over c, z upon 1 minus z upon 1 plus z dz, plus integral over c, z upon 1 plus z upon 1 minus z dz. Here, considering this as the singularity, what you have to do is that you have this 2 pi I, evaluate this quantity at z equals minus 1, then plus integral 2 pi I, then you will have to evaluate z upon 1 plus z at z equals 1. Just evaluate and take a sum, that is going to be our integral value. Okay, these things are not given in our textbook just because we know how to do the contour integration. Only the new ideology is explained. If you are given with some situation of this form, you will have to work accordingly, right? So here, if you just proceed and find out the answer, what would you get? So you can take 2 pi I as a common quantity. So when you substitute minus 1, it is minus 1 upon 1 minus of minus 1 is plus 2. Plus here you have this 1 and upon 2. So you can very well see that this is turning to be 0. Okay, this integral value is 0. This is of no issue. Right, this can happen. It is not necessary that we must always get a positive value or some quantity inside it. Even it can be 0 as well. Right. So moving further, we are going to talk about the extension of Cauchy integral formula. Okay, so we have just seen what do we mean by the Cauchy integral formula and how are we going to extend this. So by extension, what do we mean by this? We have just seen that your Cauchy integral formula can be used to evaluate the function value at a particular point with the help of an integral. Okay, suppose if you have to find the derivative of the function at some point, even that can be obtained using some other integral. That is what we are going to uh, do here. Okay, for which basically let us suppose that this function f is analytic everywhere inside and on a simple closed contour C, which is taken in the positive sense. Okay, by Cauchy's integral formula, the expression that we have just derived, right? So that is Cauchy integral. Okay, I forgot to tell you this. So it is specified, but this theorem is the Cauchy integrals formula. Okay, So if you are asked to derive Cauchy integral formula, you will have to prove this theorem. If you are asked to find out state and prove a theorem on Cauchy integral formula, then also you will have to do the same thing. Okay. So by Cauchy integral formula, what do we have? We have f of c naught equals 1 upon 2 pi I integral over c f of c dc upon z minus z naught. So we are just going to change the notations inside it. Okay. So I need it for the general case. That is why I am changing this to z. So all the z is changed to s. Just a change of variable. Okay. Here the point z is interior to c, and s denotes points on c. Right. So here, if you just differentiate equation 1 with respect to z, we get what f prime of z equals, it's just 1 upon 2 pi I integral over c, and here what would you get? That is independent of this quantity. So we have s minus z whole square, and we'll have minus that is coming out, and when we differentiate s minus z, we would get that minus goes out. So this is what we expected to get, right? So here, did I use any rule? No. I don't know if I don't know the differentiation process that I did is right or not. Even I am not aware of this. Okay. So we expect this to be our derivative value. So this is what we have. We are going to prove in the rest of this proof. Okay. So to verify f prime of z exists and equation 2 is valid, so we'll have to do this. So let d denote the smallest distance from z to points s on c, and we are going to use equation 1 to write the following. So what is it? F of z plus delta z minus f of z upon delta z. Okay, in order to write this, okay, we have 1 upon delta z, that we write it outside integral over so we have this 2 pi I as well, right? So 1 upon this 2 pi I integral over c f of s ds, and what, s minus z minus delta z dz minus 1 upon 2 pi I integral over c f of s ds upon s minus z. That's it. Right, this is what we have. So did I miss anything? Okay, nothing. So here, how we are choosing, I said that we are going to choose d. How are we going to choose is that, let this be our contour. Okay, we have the point z somewhere here, when we take z plus delta z, it is somewhere here. It will have to move a smallest quantity, right? So suppose this is my point S, this is my so just a minute. So we'll have to choose in such a way. How did we choose is that this is z, this is z plus delta z. Okay, this distance is absolute of delta z. Okay, and this is the point S, means we have this distance to be the absolute of S minus z. Okay, and your d has to be smaller than this S. We'll have to choose in such way. Okay, so now if you just look at this expression, this f of s is a constant. Okay, I mean, sorry, this is not a constant. I mean to say that this f of s ds is common in both the integrals, and 1 upon 2 pi a is also common. So we can just rewrite those things to bring f of z plus delta z minus f of z upon delta z. This quantity may be written as 1 upon 2 pi I integral over c 1 upon s minus z minus delta z minus 1 upon s minus z multiplied with f of s upon delta z ds. So it can be written like this. Now we'll have to simplify this quantity. How are we going to achieve this? We'll have to take the LCM. So integral over c, if you just take the LCM, you would get s minus delta, sorry, s minus z minus s plus z plus delta z upon s minus z minus delta z multiplied with s minus z. Okay, and then f of s delta z ds. In the numerator we'll be left with only delta z, and that can be cancelled with this delta z, and this is 1 upon 2 pi I integral over c f of s ds upon s minus z minus delta z multiplied with s minus z. So this is what we have, and here your 0 is small, your delta z is a smaller quantity than d. Okay, now what we are going to do further is that uh, we consider f of z plus delta z minus f of z upon delta z. I just subtract a particular quantity on both the sides. Integral over c f of s ds upon s minus z whole squared. So it is 1 upon 2 pi I. So 1 upon 2 pi I have taken common. I am just directly writing things here. So this is integral over c f of s ds upon s minus z minus delta z multiplied with s minus z minus integral over c f of s ds upon s minus z whole squared. So this is what we have. Now we'll have to simplify this as well, right? How shall we do that? So is it possible to do that? Yes, of course it is possible. So 1 upon 2 pi I. What should we do? We will have to just take LCM to this as well. So when we take LCM, we would have s minus, so s f of s minus z f of s, and when we do this one, minus s f of s plus z f of s, and we'll have plus delta z f of s everything upon s minus z minus delta z multiplied with s minus z squared, and finally we have this ds. Okay, this is what we have. So this and this gets cancelled, this and this gets cancelled, and we are just left with 1 upon 2 pi I integral over c delta z f of s ds upon s minus z minus delta z multiplied with s minus z whole squared. Right? So we have this and we mark this as equation 3. Hope I am continuing with the right numbers. Okay. Next, we let m denote the maximum value of absolute of f of s on C, and observe your distance absolute of s minus z is bigger than or equals d, and absolute of delta z equals this is smaller than d. Okay, so what we have is that absolute of s minus z minus delta z may be written as absolute of s minus z minus delta z, which is bigger than or equals absolute of absolute s minus sigma, sorry, s minus z minus absolute of delta z, which is nothing but bigger than or equals d minus absolute of delta z, which is a positive quantity. Right? Usually we take less than or equals. Why are we taking bigger than or equals here? Just because when we take the estimate, we have this quantity in the denominator. So if you look, if we just identify a bigger than or equals case, when we take the reciprocal, it becomes the smaller than or equals case. That is why we have taken bigger than or equals here, right? So now using equation 3, by equation 3, absolute of integral over c delta z f of c dz upon s minus z minus delta z multiplied with s minus z squared. Just a minute. So we have f of s ds only, right? So did I write it right? Yeah. So this quantity is smaller than or equals. What is delta z? That is bounded by. Okay, let me just write it as absolute of delta z, and what is the maximum value of this quantity? That is m, and in the denominator we have d minus absolute of delta z squared, this quantity squared, and this is nothing but simply d squared multiplied with the length of the contour L. Okay, so all the things are specified, only L is not specified. So that is why we are specifying L is the length of C. Okay, as your delta Z approaches 0, we get your this integral your this integral value is equal to 0. Consequently, your limit delta z approaches 0, f of z minus f of z naught upon z minus z naught minus 1 upon 2 pi I. Even if you take a limit delta z approaches 0, this does not involve any delta z, so it remains as it is. So s minus z whole squared, this quantity equals to 0. Therefore, this is what, by the definition of derivative, this is your f prime of z. Okay, so here, just a minute. Z plus delta z minus f of z. This is the thing we have. Your f prime of z is nothing but 1 upon 2 pi I integral over c f of s ds upon s minus z whole square. So this is the value of f prime of z, right? So if you have to find it in the general case, so the general case I am leaving as an exercise. So this general case is nth derivative of z is n factorial upon 2 pi I integral over c f of s ds upon s minus z to the power n plus 1. This is true for n equals 1 to till etc. So with which, if you have to find out the integral value of this form, if you have to find out the integral value of this form, this is 2 pi I upon n factorial times of nth derivative. That's it. So here, if you want, you can just change the notations to f of z naught. So here f of z dz and z minus z naught at a particular point we are talking. That's it, right? So if let us see some example. Okay, so the first example is, if c is a positively oriented circle, absolute of z equals 1, and the function f of z is given to be exponential of 2z. Find integral over c exponential of 2z upon z to the power 4 dz. So this is what we'll have to do. And when we get into the solution, we see that integral over c exponential of 2z upon z to the power 4 dz may be written as integral over c exponential of 2z upon z minus 0 to the power 4 dz. Okay, so the 0 is a member of this circle. Okay, this is inside the circle. So by the extension of Cauchy integral formula, what we have is this integral over c exponential of 2z upon z to the power 4 dz is, so we have to consider this as n plus 1. So in the integral what we have is z minus z naught to the power n plus 1, right? So we take it as that. So here n plus 1 is 4. So our n plus 1 value is 4. So it becomes what? 2 pi I upon n factorial, that is 3 factorial, and nth derivative, so third derivative of this function evaluated at the point 0. So this is 2 pi I upon 6, and when you differentiate this quantity for 3 times, first time when you differentiate you would get 2 outside, second time you would get 1 more 2 outside. So it is going to be 2 cube times of exponential of 2z evaluated at the point z equals 0. So 16 pi I upon 6, exponential of 0 is 1. So it is 8 by I upon 3. So this is the value, right? The second example that we are about to see is uh, we know that integral over c dz upon z minus z naught is 2 pi I. So with this ideology, that is the extension of Cauchy integral formula, can we find out, okay, what is the c, where c is any contour that consists of z naught. So this point z naught has to be inside c. Okay, so with which can we prove integral over c dz upon z minus z naught to the power n plus 1 is 0. Yes, of course, it is 2 pi I upon n factorial and the nth derivative of function at the point z naught. What is the function here? Here f of z is 1. Therefore, nth derivative of z is 0 for all n. Right, this is going to happen. This proves integral over c dz upon z minus z naught to the power n plus 1 equals 0. With which I conclude this lecture. In the upcoming lecture, we are going to talk about some consequences of the extension. Okay, we have just seen the extension of the Cauchy integral formula, and based on that, we are going to see some consequences, and we will work out few more problems on these ideologies. Thank you.